Article: the principle of virtual work for the forces acting on a particle. If the system of the forces on a body or a system of bodies be in equilibrium, and if the system is supposed to undergo a small displacement consistent with its geometrical conditions, the algebraic sum of the virtual work done by the system of forces is 0. Conversely, if the algebraic sum of the virtual work be 0, the forces are in equilibrium. Proof: let F1, F2 and so on Fn be the number of the coplanar forces acting on a particle at O. Let x1, x2 and so on xn and y1, y2 and so on yn be the resolved parts of the forces along two mutually perpendicular directions OX and OY respectively. OX, x dash, OY, y dash, F1, F2, F3, Fn, O dash, HK coordinates. This is OL and this is OM. Let x, y be resolved parts of their resultant are along OX and OY respectively, equals to x1 plus x2 plus x3 plus so on y1, y equals to y1 plus y2 plus y3 and so on, and r square equals to x square plus y square. Let the forces of displace the particle from O to O dash so that O dash is the virtual displacement. Let HK be the coordinates of the points O dash. Refer to O as origin, so OL equals to H and OM equals to K. So virtual work done by the force F1 equals to the algebraic sum of the virtual work done by its resolved parts of x1 and y1 equals to x1 h plus y1 k. Similarly, the virtual work done by the forces F2 equals to x2 h plus y2 k, so on. Virtual work done by the force Fn equals to xn h plus yn k. So the algebraic sum of the virtual work done by the system of forces equals to x1h plus y1k plus x2h plus y2k plus x3h plus y3k plus so on equals to h into x1 plus x2 plus x3 plus k into y1 plus y2 plus y3 and so on, so equals to h into x plus y into k into y. Equation 1, the condition is necessary. Let the particle be in equilibrium, so r equals to 0, x equal, which implies x equals to 0 and y equals to 0. So from equation 1, the algebraic sum of the virtual work done by the forces is 0. The condition is sufficient. Let the algebraic sum of the virtual works done by the system of the forces acting on the particle for any small virtual displacement be 0. So hx into ky equals to 0. This is true for all the values of hk. So x equals to 0 and y equals to 0, which implies r equals to square root of x square plus y square equals to 0. So the system is in equilibrium.